This is a demonstration of our AI-based markerless three-dimensional pose estimation application developed by the engineering health team. In this video, we used a system consisting of 6 mobile phone cameras calibrated using a checkerboard. This application can be used with any number of cameras, but at least 2 are needed for three-dimensional reconstruction. In this application, the MediaPipe pose estimation algorithm is used for pose estimation, but it can be customized to work with any other pose estimation algorithm. As shown here, the recorded videos of the participants' movement are fed into the application, and the joints coordinates are extracted. Then, using the previously calculated projection matrices and some data enhancement techniques, we reconstruct the three-dimensional coordinates of human joints. Here, we can visualize the three-dimensional coordinates of the reconstructed human joints. Our application can compute joint angles and segment orientations in the three-dimensional space. To enhance the user experience, we provide the option to animate the performed tasks with or without local coordinate frames, giving users the flexibility to view and analyze the data according to their preference. For instance, let's focus on the analysis of the left knee joint's movement during a lifting task. This will allow us to examine the animation more closely, particularly the orientation of the left upper leg in three-dimensional space. In the accompanying graphs, we can observe the orientation of the local coordinate frame attached to the upper leg with respect to the global coordinate frame, represented by dashed lines in the scene. In this model, the local y-axis is along the segment length. The x-axis indicates flexion, extension of the segment, and the z-axis represents internal, external rotation of the thigh segment. The graph indicates a maximum clockwise flexion of 60 degrees with respect to the transverse plane. Now, let's turn our attention to the shank segment. As depicted in its graph, it exhibits an approximate 35-degree clockwise flexion with respect to the horizontal plane. In the following tab, we have the capability to compute intersegmental planar angles. By selecting the desired limbs from the drop-down menu, the graphs reveal the differences between the segment's orientations, or in other words, hypothetical joint angles. In this case, the knee joint angle, as illustrated in the graph, both flexion angles are calculated as positive. However, upon observing the animation, it becomes evident that they are actually rotating in opposing directions. To accurately calculate the intersegmental angle, we must adjust one of them accordingly. Simply check the reverse box next to the distal limb and then proceed to recalculate the intersegmental angle. As indicated by the first and second graphs, the intersegmental angle between the thigh and shank, or the knee joint during the lifting task, is approximately 75 degrees. Additionally, the internal-external rotation of the shank to the thigh is approximately 30 degrees. To have a sense of the accuracy of these calculations, we can return to the previous tab and select the left knee from the absolute joint angles section. In this context, the graph demonstrates that the absolute knee angle is approximately 80 degrees. Also, the square root of the sum of the squares of the second and third graphs in the intersegmental joint angles also yields an approximate value of 80 degrees. In the following sections of the application, you have the capability to compute the projection of joint angles and Euler angles, which are required for inverse dynamic calculations.